he had almost all possible positions at the Warwick University, and in 2017 he moved to the Imperial College. Martin has a long list of awards. I won't mention all of them to take too much time. I'll just say that in 2008 he got the Whitehead Prize from the London Mathematical Society, which is the corresponding of the SBM in Brazil. In 2014, he got the Fields Medal, together with Arthur Avila in Seoul. And in 2020, he got the Breakthrough Prize. He is now the chair of the program committee of the ICM 2022. He got, well, I would say that his most important contribution regards renormalizing stochastic partial differential equations, in which he developed a theory which makes sense, could give sense to nonlinear stochastic partial differential equations. And if you are interested in understanding his contribution, I would recommend Zaitoun's Laudatio lecture, which is available on YouTube, and which explains essentially Martin's contribution. Martin has a strong connection to Brazil. Alberto Ohashi, who was professor at Paraíba and now he's professor at Brasilia, was his first PhD student in a co-orientation with Paulo Rufino from the Unicamp. Also, let me mention that Dirk Erhard was his postdoc. He's now a professor at the University of Bahia, and both Ohashi and Erhard are working on the theories developed by Martin. Martin is also a regular visitor. Let's say that his last mini course was given at the Probability School last year in 2020. So it's a great pleasure to have Martin today with us. And as you can see, he will speak about toward the Euclidean YangMills theory. Martin, thank you very much.
Thank you very much. Thanks a lot, Claudio, for the really nice introduction. And thanks a lot to the organizers for inviting me. It's a pleasure to be here. Well, it would have been even more of a pleasure to really be in Brazil in person. It's too bad that that can't happen at the moment. It will probably happen at some point in the future, hopefully. So the work I want to talk about today is, so it's joint work with AJ Chandra, who is also at Imperial College, Ilya Shevirev from Edinburgh, and Hao Shen from University of Wisconsin-Madison. And okay, it doesn't really matter if if you haven't heard before the various words that appear in the title. Well, you've certainly heard the word Euclidean, but maybe not in the same context. Then I'm going to try to explain what this is about.
Martin, just let me tell the audience that if they want to ask questions, they can ask questions on YouTube, and then I will transmit them to you. Sorry.
Okay, great. Thanks. Yeah, so feel free to ask questions. So that, and if there's a question that is of sort of general importance or which might be useful for other people, then Claudio, feel free to interrupt during the lecture as well. So in this context of Euclidean quantum field theory, so essentially Euclidean quantum field theory, the idea is that you try to build quantum field theory by making time imaginary, which at a formal level simplifies sort of Feynman's path integral construction. So that's the starting point. I'm not going to talk about much on the justification of when you're allowed to do that and how you're allowed to do this, but this was essentially figured out by people like Osterwalder and Schrader. So in the was it probably in the 70s or so. So this is kind of a well-known procedure, and the starting point that I'm going to take is that you take a functional Lagrangian on a space of fields and the sort of things that you have in mind, right? So a field is just a function from some underlying state space. So the underlying space is going to be your space time, So a field could be, for example, a function from sort of RD to R. And then the sort of thing that you should have in mind is an integral over the underlying space of some local quantity of the field, right? So the simplest example would be, for example, to take gradient phi square, right? So that would be an example, such a Lagrangian. You could also imagine, for example, adding here a pointwise function and so on, right? So that's the kind of things that you should have in mind. And in Euclidean quantum field theory, basically what you want to do, at least in constructive Euclidean quantum field theory, is you would like to build a probability measure on the space of fields, which at some formal level should be interpreted as e to the minus the action times Lebesgue measure, right? So this d phi here, you should think of this as being Lebesgue. And it's Lebesgue, well, it can't really be Lebesgue, right? So this looks like an expression where you have a reference measure and you have a Radon-Nikodym derivative. But of course, you're not allowed to interpret it in that way because it's well known that there is no analog of Lebesgue measure on infinite dimensional spaces, right? So if you take an infinite dimensional vector space and you ask yourself, can you build a sigma finite measure which is invariant under all translations? Then the answer is just going to be no, right? So this measure doesn't exist. But of course, what you can hope to be able to do is to do some sort of approximation, right? So if the underlying space here is RD, then you could hope to replace RD by ZD, for example, or say a finite chunk of ZD. And then, well, of epsilon times ZD, right? So you discretize your space and you take a large box. And then your field, the natural discretization of your field is now just an element of some very large Rn. And if you have a natural discretization of that Lagrangian, well, then at least the discrete analog of that measure makes sense, right? If S is sufficiently coercive, right? So if S kind of grows in all directions in a way. And then the hope is that you can somehow pass to the limit, right? And then, of course, if you want to pass to the limit, then you also have to ask yourself, you know, if there is a limit, does the limit actually depend on how you discretize things, right? So if you replace RD by a square lattice or a hexagonal lattice or some other way of smoothing things out, do you actually get the same limit? Of course, that sort of measure also shows up in statistical mechanics a lot, right? So Gibbs measures in statistical mechanics have exactly the same sort of form, where S now is interpreted as a Hamiltonian. But in the example that I'm going to discuss today, so the example of the YangMills measure, that at least to the best of my knowledge, it doesn't really have a good interpretation on the StatMech side. So it's really, the motivation really comes from, if you want, Euclidean quantum field theory and not StatMech. So, okay, so now what is YangMills? So in the case of YangMills, the fields are going to be something a little bit more complicated, okay? So they are not going to be like the example I just mentioned, where the field would just be a function from space-time into the real. So here the setting is that we have we fix a Lie group, G, so a compact Lie group. So the simplest example you can think of is the one where G, for example, is equal to U1, which is basically the unit circle. With complex multiplication. But of course, the interesting cases are not going to be U1. The interesting cases are going to be the ones where G is non-abelian. So as usual, I write sort of Gothic G for the Lie algebra. And then the state space, the space of fields for YangMills is naturally identified with one forms that take values in G. Okay, so a one form is basically a function with values in the cotangent space. So it's so that at every point you can feed it a tangent vector and it spits out normally, a normal one form spits out a number. And this is a G valued one form. So it's a one form that you feed it an element of the tangent space at every point and it spits out an element of the Lie algebra G. Okay, and the way you should interpret this, right? So this one form A, one should really interpret this as a connection on D-dimensional space. So here I write torus, it could be RD as well, but the results that we have on the torus. So you take the space torus times G. So for example, in the simplest case, for example, in D equal 1, right, your underlying space is just a line. And now at every point of the line, you sort of attach a copy of G, right? So that now you have a copy of G at every line, at every point of this line. And what you should, the picture you should have in mind here is that you view this really as a principal bundle and not actually as a product space. And that basically means that at every point you forget about, you know, G has one distinguished element, which is the identity, right? You forget about which element of G is the identity. So you don't think of G as a group, but you think of G as a space on which G itself acts as its group of symmetries, okay? And the way it acts is just by multiplication on the left, right? So you think of G here not really as a group, but just so, for example, in the case of U1, you really think of it as a circle, and the circle, you know, with the group of symmetries that are the rotations of the circle, and that's the elements of U1. Okay, but on the circle, there's no distinguished point, right? Every point on the circle sort of looks the same. And so what this means is that if you kind of move, right? So if you move in the, on the underlying sort of downstairs on the torus TD, there is a priori no canonical way of turning this into a motion on this full space because you pretend that you don't know which element here is special, right? So, for example, if you, right, so if you take a line here, a curve in the underlying space, so on TD, and you want to sort of lift that curve to TD times G, so let me draw in pink. So for example, the starting point here, I lift it to some point on this copy of G. And now I want to move in that product space in such a way that, you know, at every time T, the point here lives in the fiber that's above the corresponding point on the green curve. Well, there's no canonical way of doing this a priori if I haven't, you know, fixed an identification of these different copies of G. And the connection is basically what allows you to do this infinitesimally, right? So you move infinitesimally in a direction downstairs. And so I have to tell you how to actually move in the fiber that goes above it, right? And the way you move in the fiber, so I have to specify an element of the tangent space of the fiber, and the tangent space of the fiber at every point is sort of canonically identified with the Lie algebra, right? So that's why here the natural, so connections are identified, if you want, with one forms that take values in the Lie algebra. Once I fixed here, for example, right, so I fixed the trivialization here of this bundle. But what you should have in mind here is that really physical observables are always going to be things that are quantities that are independent of a choice of coordinates, where a change of coordinates now means, if you want, you can rotate each of these circles sort of more or less independently of each other, right? Because that's like a change of coordinates. Right? Rotating one of these circles is like performing a change of coordinates in G. And we said that that's, you know, that just in some sense corresponds to moving the origin around. And we said that there's no point that we consider to be a preferred point somehow for the origin. Right? And so all the relevant physical quantities should be quantities that are that don't depend on this operation of, locally, if you want, rotating by an element of G. Okay, and that's what's called the gauge transformation, right? So the gauge group here. So this group G is what's usually called the structure group. That's what I mentioned here. And the gauge group would be sort of curly G, which would be functions, functions from TD into the group G, right? So that's if you want coordinate transformations, but coordinate transformation that sort of fix the fibers. So they only act in the G part. And you want everything to be invariant under changes of coordinates. And so the Lagrangian in YangMills is given by the L2 norm of the curvature of this one form. And so what's the curvature of this one form? Well, what you should have in mind now is, so say the underlying space is at least dimension 2. And again, you have this sort of copy of G sitting above every point. And now imagine that you take a little loop, a closed loop down in R2 around some point X. And now you lift that, you use A in order to lift the loop to the bundle, right? So then you get a little loop upstairs, but the loop upstairs doesn't necessarily close up, right? So the way the connection works, it just locally sort of tells you how to move whenever you give it a direction, and it doesn't have any reason to be integrable, right? So if you actually go back on a little loop, you might move. So if the loop is sort of diameter epsilon, you would move by about epsilon square somehow in the direction of G. And the amount by which you move here is what's called the curvature of the form. So that's a 2 form, because basically you specify a plane in which you take that little loop. And for every plane, you get an element of G of the Lie algebra, which tells you, by how much, if you take a little loop in that plane, by how much this operation makes you move sort of in the tangent space of G. Okay, and it turns out that the amount by which you move is essentially proportional to the area of the loop, and the amount by which it is proportional to the area, that's called the curvature of A. Okay, and so that's what I write as FA here. And if you just do the calculation, you find, at least in local coordinates, you find an expression for it, which is given here, which is essentially, if you interpret A as a 1 form, this would be like the exterior derivative of A. Right, so this is just dA. And then here you have this additional term that is relevant in the case where G is non-abelian. Right, so this bracket here is the Lie bracket in the Lie algebra here. Okay, so now that's your Lagrangian. And you see, to some extent, it looks a little bit like the example I gave at the beginning, right? The example I gave at the beginning was the Lagrangian would just be gradient phi square, the L2 norm of the gradient of phi. And so here, well, your field is A. This is essentially some kind of derivative of A, right? So here you have differential of A, and then there's another local function of A, and you take the square of that, you integrate over your space. Okay, so it's more or less of the type of what I mentioned at the beginning. But what's special here is that this curvature, one can check that that's actually an intrinsic quantity, right? So the curvature is basically invariant under the action of the gauge group, or at least it sort of acts trivially on it just by conjugation. So this gauge group, right? So the gauge group, remember I mentioned just one slide earlier, that gauge group is just the name for these coordinate changes that fix the fiber, right? So at every point you give yourself an element of G, and you view this as a sort of rotation of the fiber that's allowed to depend on the base point. And And of course, if you interpret A as a connection, right? So if in this picture of A being giving you somehow a procedure for performing these horizontal lifts, then you can figure out how this is going to change under changes of coordinates. Right? And if you do that, well, you find that A somehow changes in this way. So it changes by pointwise conjugation, but there's an extra term. And that's, if you want, a reflection of the fact that A, even though we interpret it as a one form, it isn't really a one form. It is really a connection. And so it transforms differently under changes of coordinates from one forms. So one forms would just change like this without transform like that without this additional term. But FA, one can do the calculation just using that formula and the explicit form of the action of the gauge group. One can find that FA just transforms like a two form. So when you act with an element G of the gauge group onto A, then FA just gets conjugated by G pointwise. And then if the norm here, so here I didn't specify which norm one takes, under the algebra, but the natural thing, if you have a compact Lie group, then there's exactly one possible choice of norm, well, modulo scalar multiples, but there's basically one possible choice of norm under the algebra, which is invariant under the adjoint action of the Lie group. So you take that norm. So there's a natural norm on G. So that's the norm that shows up here. And that norm has the property that it's invariant under the adjoint action. And so if you conjugate FA here with G, it doesn't change the norm. And so this quantity here is independent, if you want, on the changes of coordinates, which is sort of natural because this density here should be kind of a physical quantity. But this is a problem, right? So the problem is that, well, what this tells you, so if I do a picture of somehow like here, I have my space of connections. So now the board is the space of all connections, which is of course infinite dimensional space. And you have these orbits here that are called gauge orbits that are, if you want, all the different connections that you can get by acting on one specific connection with the gauge group. Okay, so you look at all the orbits of that specific connection under the action of the gauge group. So it's all the different connections you get after changes of coordinates. And what we just said is that the functional S doesn't depend, is invariant under the action of the gauge group. So it means it's constant on all of these orbits. Okay, but these orbits are themselves infinite dimensional, right? Because the gauge group is infinite dimensional. So these are infinite dimensional orbits. So now, the measure that we were trying to build is something like e to the minus the action, the YangMills action. And now that's a quantity which is constant on all of these orbits. And so again, the measure should somehow look like Lebesgue measure on each of these orbits. And then again, that doesn't exist because they're infinite dimensional. And so they are not linear spaces, but they're actually locally, they basically look linear. So there is no Lebesgue measure on these orbits. So again, no Lebesgue measure on infinite dimensions. So basically such a measure can't exist. So how do you get around that? Well, I mentioned a couple times now that all the physical observables, so all the quantities that you're actually interested in, all the quantities that have an intrinsic meaning, they are the ones that are invariant under changes of coordinates. So that means they are the ones that are gauge invariant. So they are functions of your connection that have the property that, if you act on your connection with an element of the gauge group, the function doesn't change. Okay, so like, for example, the L2 norm of the curvature. So that would be an example of such a physical observable. So the physical observables, they don't depend right? So they are constant as well on all of these gauge orbits. And so what you would want to do in a way is you would want to kind of just collapse these gauge orbits to a point, right? So the idea is you would just say, oh, here I have an equivalence relation. I just say, well, you know, these two connections are equivalent if there's an element of the gauge group that goes from one to the other. And then the measure that you want should really be a measure on the space of equivalence classes and not actually on the space of connections, right? So that's kind of the idea. So a typical example here of observable, so the most important, if you want, class of observables in this business is what's called the Wilson loops. And so here what you do is you take a closed loop in the underlying space on RD or TD. And then you do exactly the same procedure as before. So you look at what's called the holonomy of your connection along that loop, which is, you know, you take the horizontal lift of the loop, you look at by how much, by the time you're back over the same fiber, by how much you've moved. So that's this quantity here. And then you stick this into a class function. So a class function is any function on the gauge group, which is invariant under conjugation. And if you do this, then what you get is invariant under changes of coordinates. So that's basically how the action of the gauge group on the connections was defined. It was designed in such a way that these holonomies are basically invariant. So that's the typical kind of observables that you should have in mind. And they are, I mean, to some extent, they're basically exhaustive. So in the sense that you can actually distinguish gauge orbit by the values of if you know all the Wilson loops, then you can actually distinguish different gauge orbits. And so, yeah, so you would like to somehow interpret this measure e to the minus YangMills action as some kind of measure on this space of gauge orbits. And well, it's still not clear how to do that, right? It's not clear what a good state space is either, right? So because at some point, if you want to, you know, really interpret this as an actual bona fide probability measure, you know, you have to actually get technical and say, you know, what is the actual space of connections that you take? What is the actual sigma algebra that you're looking at, and so on. And here it's not, you know, it's not going to live on smooth connections, so you cannot just take C infinity functions or something like that. It's not even going to live on continuous functions. And then, you know, things like, for example, Wilson loops, it's much less clear what they actually mean if your A is not a function anymore. You know, you end up in all sorts of difficulties. Now, let me just go of course, this is a sort of classical problem, what I've been telling you so far. And there's been a lot of previous work. So let me just give you, well, I'm not going to mention sort of all the previous work in this area because it's, you know, that will probably take an hour by itself. I just want to mention like a few of the works that are closest to what I want to talk about. So in the late 70s, Bridges, Fröhlich, and Seiler, they actually built, if you want, a abelian YangMills field. So in the abelian case, of course, you know, that Lie bracket was 0. And in that case, the YangMills action, the pure YangMills action is just quadratic. And then, of course, any measure which is e to the minus something quadratic times Lebesgue measure is a Gaussian measure. And then you can just guess its covariance, right? So if you have e to the minus some formal expression, that expression is supposed to be the inverse of the covariance. So that's not terribly interesting. So what they were looking at is actually a YangMills field which interacts with an additional field, right? So in some sense in this business, pure YangMills, which is what I've described so far, describes the vacuum somehow. Right? So if you want an actual physical theory that has particles in it, these particles would be described by additional fields. And so that's what Bridges, Fröhlich, and Seiler did in 2 dimension. Okay, so you take YangMills, abelian YangMills, which is the easier one, but then you couple it, to a matter field, if you want. And so that was constructed sort of in the late 70s. So then for pure YangMills, but non-abelian, there's sort of Migdal in the 70s came up with essentially guesses for the joint moments of the Wilson loops of observables. Right? So that's sort of just like formal calculations that allow you to actually guess the joint moments in 2 dimensions. And then a number of people, sort of Driver, Gross, Kings, and Gupta, and so on, in the late 80s, they actually built, they built a proper probability measure out of that, if you want, on a space which allows you to have Wilson loops defined. And Sengupta there in the 90s actually did this in the non-abelian case as well for pure YangMills. And that has actually had kind of a renaissance in the 2000s by the work of Thierry Lévy. And so there have been actually quite a lot of work in the last 20 years on 2D pure YangMills, because in that particular case, there's some kind of integrable structure. So you actually have an almost explicit description of the joint law of all the Wilson loop observables. So you can actually describe that joint law quite explicitly. And Chevyrev recently, so he actually in some sense went back to the space of connections and showed that it is possible to actually find a state space for the actual connections, which on the one hand is small enough so that the Wilson loop observables make sense on it, so they can be realized as sort of continuous functionals on that state space. On the other hand, you can actually build a probability measure on that space, which has the property that if you then look at the joint law of the Wilson loops, you do get the expression that was derived by all of these people. Okay. So you can actually lift that back to a space of connections. In 3 and 4 dimensions, much less is known. So of course, the physically most interesting case is the 4-dimensional case, right? Because the underlying space is really your space-time. Okay. Unfortunately, in 4 dimension, at this level, mathematically, very little is known from this probabilistic perspective. In 3 dimension, there's some work by, there's a series of works by Balaban in the 80s and by Federbusch as well. And they used an approach essentially a bit a la Feldman, Glim, and Jaffe to try to sort of build a renormalized Wilson loop observables in 3 dimensions. And actually there's some work by Magnan, Rivasso, and Senora in 4 dimensions as well. But it's not clear how this relates to the perspective that I've been trying to give you so far. So it's not clear at all that you can actually turn this into a probability measure on some space of gauge orbits or something like that. And then there's also some very recent work by Kao and Chatterjee, which hasn't been published yet. It's not even on arXiv, where they make an attempt, if you want, at describing what would be a decent state space for these gauge orbits. But the space that they propose is extremely large. So in some sense, if in the analog with sort of classical field theories like just the free field or the 5-4 theories, the analog of their space would be the space of all possible distributions, which is a very large space. Of course, the space being very large makes it easier in principle to build a probability measure on it, but it makes it harder to, for example, have something like Wilson loops or things like that, right? So when you want to extend something continuously from something which is defined on smooth elements, you want to sort of extend it continuously on some larger space, then of course the larger the space, the harder this is. So one has to always sort of try to balance things here. Okay, so the approach that we tried to follow was first proposed by Parisi and Wu in the mid-80s, and it goes usually under the name of stochastic quantization. And the idea there is that, well, in finite dimensions, okay, so if you're again in the case where phi is just an element of Rd, of Rn, say, and S is just some nice smooth coercive function on Rn, then the measure e to the minus s can be realized as the invariant measure of some stochastic gradient flow, right? So this here is, okay, so this is the probabilistic way of writing. So you can kind of think of this as being, kind of written it like that if you want. So this is just the gradient flow for S, which sort of tries to find local minima of S. But then you perturb this by a white noise. So this becomes stochastic. So you have this white noise that moves things around randomly, that sort of prevents the dynamic from just getting stuck in local minima. And well, it's a sort of classical calculation to check that if, you know, S is nice enough, then whenever you start with an initial condition that is distributed according to this measure, and then you run it under this evolution, then at later times it's distributed according to the same measure. So that measure is invariant for this evolution. And furthermore, it's the only invariant measure for that evolution. Okay, so you can characterize this measure as being the unique measure that is invariant for this stochastic gradient flow. And so here just a remark. So of course, if I write gradient, that means that somewhere I've chosen a metric because intrinsically the differential of a function of your state space belongs to the cotangent space. So you have to somehow turn it back into the tangent space. So here you fix the metric implicitly. But then your noise here pushes you around in all directions of your state space. And there, in principle, you also have to, you know, specify in which way it pushes you around. And that implicitly also determines a metric. Right? The metric is the metric for which the way it pushes you around is kind of round, if you want. It's the same in all directions. And implicitly, when I write this here, it means that the two choices of metric here have to be the same. So, okay, so that's the idea. So the hope there is that now, well, maybe what you can do is you can actually look at this kind of stochastic gradient flow for your Euclidean quantum field theory, and then you can give a meaning to this stochastic gradient flow. And if you can give a meaning to that stochastic gradient flow and show that it has a unique invariant measure, then that's a candidate for the measure that you're after. Okay, so that's the basic idea, which Parisi and Wu proposed in the 80s. And so in the case of YangMills, if you look at that gradient flow, then what you get is, well, it's the expression I wrote down here. It doesn't really matter too much what the specific expression is. What matters is that it's of this form. So it looks somewhat parabolic. So it looks like a heat equation. There are lower order terms, so lower order in the sense that they have sort of less derivatives appearing. So here there are terms in A and derivative of A, and there are terms in A cubed. So there's sort of a quadratic term which is bilinear in A and its first derivative, and there's a term which is trilinear in A. So they have at most one derivative. But the terms with two derivatives, there's a Laplacian here, but there's this additional term which is a bit annoying. And that's kind of a reflection of the fact that, remember, these gauge orbits, they are such that formally our YangMills measure is supposed to be Lebesgue on these gauge orbits, and that's something that we don't like. And of course, here we just brutally wrote down this stochastic gradient flow. And so formally it has the same property, which is that it has this property that the invariant measure should be kind of uniform on these gauge orbits. And that means that, you know, your gradient flow is always going to be sort of perpendicular, if you want, to these gauge orbits. But the noise here pushes you around in all directions. And so it just pushes you uniformly in all the directions along the orbit. And therefore, on the orbit, there's going to be no preferred location, right? It's just going to diffuse somehow along the orbit. And so the invariant measure should be kind of Lebesgue along the orbit. But we don't like that. And so the idea, the trick, which was, so that's a trick which was sort of introduced by de Turck in the context of the Ricci flow, and then by Donaldson in the context of YangMills, is, well, this equation we wrote down here, you can actually formally see that it is gauge invariant in the sense that, you know, if you take 2 points on the same orbit, and you look at the solution to this equation, at least you pretend that it has a solution, and you do all of this formally. If you look at the solution to this equation starting from A, and then you just conjugate, you just apply the that element of the gauge group to it pointwise, right? So you just apply G to the solution, then that gives you the solution starting from AG. Okay, so if I have 2 points here, there's 2 things I can do. So on the one hand, I can take this as an initial condition for this equation, and I can look at what I get. On the other hand, I can take this guy as an initial condition, look at what I get, and then act with G on it. So I get another process that also starts from here, and the claim is that the 2 are the same. Okay? Of course, that's, again, it's something which, it's a claim which doesn't really make sense because we haven't even given a meaning to this equation, but it's a purely formal calculation. So you just pretend everything makes sense, and you see that you just get the same equation back. Right? So what this tells you is that you can, at least formally, what you could do at every point, you can modify the equation. And so at every point, I could actually just add a vector field that points in the direction tangent to the gauge orbits. And since, you know, moving in the directions tangent to the gauge orbit doesn't change anything, because the solution starting from here is just the solution starting from here that's moved over, right? So that I can just do that all the time. And then, you know, if I'm lucky, I can actually do this in such a way that the equation has nicer properties. Okay? And it turns out that, well, basically, so what, you know, if you kind of think about what does it actually mean, what are the directions that are tangent to the gauge orbit at every point, you find that these are all terms of this type. So all the terms that are sort of a gauge covariant derivative of any function here of A. Right? So this is any functional of your connection, and you take this gauge covariant derivative. And so then the specific choice here, which is some kind of minus a divergent, gives you an extra term. So, right, so that creates an extra term in your equation, which at every point just points in the direction sort of tangent to the gauge orbit, and which has the property that it cancels out this term here, which you didn't like, which made the equation sort of non-parabolic. Okay, so after doing this, you end up with an equation which is still sort of the same form here, but now the highest order term here is just the heat equation. Okay, so the equation is of the form heat equation plus some nonlinear terms, plus white noise. And so now this is an equation that one has much better chance of being able to analyze, at least in dimensions below 4. But from a mathematical point of view, you still have, a number of basic questions, which is, how do you actually interpret this equation? So if you take just the heat equation with that noise, so the solution to that equation is, as soon as you're in dimension 2 or higher, the solution to that equation is actually distributional. So it looks like, so for probabilists in the audience, it looks like a free field. Well, so that is the free field. And the free field, of course, lives on distributions as soon as you're in dimension 2 or higher. And, well, that's somehow a problem, for example, for defining Wilson loops, right? Because the Wilson loop required you to be able to compute holonomies of your connection. And that requires you to be able to restrict it to a loop. In general, if you have a distribution in 2 dimensions, you cannot necessarily restrict it to a one-dimensional loop. So it's not clear what the state space is. It's not clear how to interpret the equation either, right? Remember that here you have terms like ADA and like sort of A cube. And of course, if A is a distribution, then these terms are problematic to interpret. And then you would still, you would want to have some kind of, even if you have an interpretation of this equation, you want some sort of reality check that it is sort of the correct interpretation, right? And so what's the reality check here? So the reality check is that you would still want to have some sort of gauge equivariance. So what you would want to have, the minimum property that you want, is that if you start with 2 initial conditions that are on the same gauge orbit, and you look at the solution starting from here, the solution starting from here, and then you compare them modulo projecting on the quotient space, right? So you just, if you want to identify points on the gauge orbit, then you would want the solutions to be the same, right? So in other words, you would want, so that guy would give you a Markov process on some kind of space of connections. You would want this to project down to a Markov process on the space of gauge orbits, which like formally should be the case. The whole thing is somehow designed so that this is the case. But of course, that's just formal calculations. Okay, and so that's somehow a good reality check that tells you that there's a chance that you're doing the right things. Okay, so here, so let me just say a few words on the sort of basic problem of kind of interpreting the equation. I don't want to spend too much time on that, but so the equation, as already mentioned, is somehow of this form. And of course, what you would want to do is you would want to replace your noise by some smoothened out noise. Also, for example, you could take a discretization of the equation, right? So you could put it on a lattice. But it turns out technically it's easier to replace the noise by just some smoothened out noise, which instead of having delta functions as its covariance has some kind of smooth approximate delta functions as its covariance. And then, well, at least heuristically, there are kind of good arguments that suggest that if you just replace psi by psi epsilon here and try to pass to the limit, then in general, it doesn't converge. On the other hand, we do have, so by now we have a sort of pretty complete theory, which tells us how we should fix the equation in order to make it converge, right? And so that's this regularity structure business basically gives you a systematic way of doing that. And if we apply it to this particular equation, what it tells us is that it's possible to choose, if you add a term of this type, so just something linear in A with a constant, so this guy is just a constant, right? So that's just a real valued constant. So if you just add this additional sort of dissipation term, if you want, to your equation, but you choose this constant in the right way, then you can get a limit. Okay, then as epsilon goes to 0, you get a limit. But now you have a problem, which is that first, adding this term looks like it actually breaks this gauge equivariance. Right? So there was these formal calculations that tell you that if you start at different points on the gauge orbit, the solutions are sort of related to each other by a gauge transformation. That relies sort of very strongly on the structure of the equations. And this structure is somewhat canonical. I mean, there's basically nothing you can change that preserves that structure. In particular, adding a term like that destroys that structure. Okay, so that formal calculation is wrong when you add a term like this. So it looks like by doing this, you sort of break gauge equivariance. Furthermore, even though you get a limit, you actually get a one-parameter family of solutions here, right? Because if some choice of constants here gives you a limit, then adding 1 to the constant is also going to give you a limit, and it's going to give you a different limit. Okay, so you really get a one-parameter family of possible limits here that are kind of parametrized in some sense by the finite part of that constant. Right? So now you have a sort of double problem, which is that on the one hand, you don't have like one solution anymore, but you have a one-parameter family. So which one's the right one? And on the other hand, it looks like you've broken this gauge equivariance property, which is sort of like almost the defining feature of the theory. So fortunately, we can kind of fix that. So here is what we can show in 2 dimensions. So we have some results in 2 dimensions, some results in 3 dimensions. In 2 dimensions, the picture is much more complete. So I'm going to just first state what we know in 2 dimensions. So in 2 dimensions, we can find, so first we can construct a nice state space for this process. And nice, it's in the sense that, well, okay, so that's going to be some of the next points, which are going to show you what is nice. Okay, so first, the space is sort of large enough to actually support the solutions, right? So that's the first property, which is that actually the convergence, so if you choose these constants in the right way, then you can converge to a limit, and it converges, in the space of continuous functions with values in that space. Okay, so you get an actual nice sort of continuous process with values in that space. So that's a space of 1 forms, but they are distributional. Okay, so in principle, they are not function valued 1 form, but they're kind of distribution valued 1 forms. Smooth connections are still dense in that space, so at least every point can be sort of interpreted as a limit point of smooth things. The quotient space is actually a nice kind of space, and that's not obvious, right? So because these are 2 infinite dimensional spaces, and you sort of quotient an infinite dimensional space by the action of another infinite dimensional space, even if they both have totally nice topologies, if they are not compatible in really just the right way, the quotient space has no reason to have any sort of nice properties, right? So for example, think of the space of continuous functions from the interval 0, 1 to R acting on L2 of 0, 1 to R by addition. Okay, so that's 2 perfectly nice spaces. The action is perfectly continuous and everything you want, right? The quotient space is absolutely horrible, right? So you're trying to quotient L2 functions by continuous functions. So equivalence classes are, like sets of L2 functions that differ by a continuous functions. The set of equivalence classes doesn't have any nice property at all. Okay, it doesn't have any good topology. Well, it has a topology because there's a quotient topology, but that topology doesn't have any nice properties. So the quotient space is not even a Borel space. So there's basically no decent measurable function on that space. Okay, so the claim here is that if we choose the space of we can choose a space of gauge transformations, which is nice in a way that's compatible. So the quotient space is actually a complete separable metric space. So it's as nice as you want. Okay. And the Wilson loop observables are continuous on that space. So even though elements of that space are distributions, they are distributions that are nice enough so that you can actually restrict them on smooth curves. And you can not only restrict them on smooth curves, you can actually perform horizontal lifts along them. Okay, so the notion of horizontal lift is actually well defined for connections, if you want, in this space. So you do have Wilson loop observables, and they are, you know, these observables are invariant under the action of. So here there's an alpha missing. And then remember here I mentioned that you actually have a one parameter family of possible limits. Well, we claim that there is a unique element in that one parameter family which is such that you recover that gauge equivariance. Right? So a priori you had this one parameter family of possible limits. Well, there's exactly one guy in there which has that property that if you project the Markov process onto the space of gauge orbits, then the projected process is still Markov. Okay, so like if you start with initial conditions that are two different points on the same orbit, then the solutions are themselves also basically always on the same gauge orbit. And furthermore, we know that one has at most one invariant measure on that space. So the bits that are missing here is that, well, so here one has uniqueness, but one doesn't have existence, fortunately. So we don't know whether that process actually has an invariant measure. And the reason why we don't know that, we don't have good long-time control. So actually, so here in point one, for the eagle-eyed people here, they would have seen the disclaimer here with the modulo possible blow up, which is that our process, our space, the space of gauge orbits here, comes with a natural kind of metric. And in that metric, there is actually a natural sort of notion of going to infinity. And we cannot rule out that it actually sort of goes to infinity in finite time. And that would prevent it from having an invariant measure. Of course, we don't expect that at all, right? It's just that we don't have a proof of it. The other bit which we don't have a theorem for, which is related to this, is of course the link back to the existing literature on two-dimensional YangMills, where there are these explicit formula for the joint distribution of the Wilson loop observables. Well, if that process has an invariant measure, then that gives you another joint distribution on Wilson loop observables, and you would want to know that they are the same. And obviously that's what you would conjecture, but we don't have a proof of that. I think obstructions are mainly technical. I don't think that there's really anything conceptual. So that's the situation in 2 dimensions, which is really quite nice. In 3 dimensions, unfortunately, okay, so I'm sort of almost running out of time. So let me just maybe show you what we know in 3 dimensions. We know somehow much less in the sense that, so we can find a decent state space. The state space is not as nice in the sense that, for example, our space of distributional connections is not a Banach space. It's not a linear space anymore, actually. And the reason is that if you take in 3 dimensions, the equation is so badly behaved that actually you cannot even find a linear space which is on the one hand large enough to contain solutions to the equation, on the other hand small enough so that the deterministic part of the equation makes sense, that the solutions to the deterministic part make sense with initial conditions in that space. Okay, so it's basically a theorem that it's not possible to find any Banach space of connections which is large enough to contain the solutions of the equation and small enough so that you can start the deterministic part of the equation with elements of that space. And so, of course, for the stochastic part, it's in some sense most harder to start it than the deterministic equation. But you can find a nonlinear space which has that property. It's sort of mildly nonlinear, but it's still nonlinear. And then we have a similar result. So again, you have this choice of constants so that you converge to a limit, and there is a unique choice so that the limit satisfies some notion of gauge equivariance. The notion here is a little bit different in the sense that we don't have a very good gauge group acting on the space. So we have smooth elements of the gauge group act on it, but then the orbits, of course, of the smooth guy are not closed. So that's not something nice to quotient by. And we do not know of a good sort of larger topological group which would contain, if you want, the smooth gauge group, and for which the orbits are closed. But on the other hand, you can basically just take the closures of the orbits, and that gives you an equivalence relation. You can show that this gives you an equivalence relation, which is non-trivial, right? I mean, in the sense that it could be a trivial equivalence relation because these orbits could sort of accumulate on each other or something, but they don't. Okay, so that you can show. So you still have a sort of notion of equivalence, of gauge equivalence, but you don't have a good action of a gauge group anymore. But we can still show that there is a unique process which has this gauge equivariance property in the sense that solutions starting from equivalent initial conditions remain equivalent, if you want, at later times, modulo a measure preserving transformation. Okay, so that's basically what we know in 3 dimensions in a nutshell. So unfortunately, much less than what we know in 2 dimensions. So one problem is that here we don't have Wilson loop observables. We have like smoothened out Wilson loop observables. Wilson loop observables are not actually expected to really exist in 3 dimensions. And that's somehow related to the fact that the 3-dimensional free field cannot be restricted to a smooth loop. Okay, so that's just an unfortunate fact. And so, right, so here are a few of the open questions that we still have. So I already mentioned some of these. And so I think this is the right time to stop. Thank you very much for your attention.
Well, thank you very much, Martin, for this very nice talk. So we are now open for questions. So I remember that if you have any question, you can ask them on YouTube, and then I will transmit them to Martin. So I will start with general questions. We have several young students watching your seminar. So I would say that if I were 20 years old, that's probably one of the fields I would try to understand and work on, because I believe that it has a very nice story to come. So what would you say for a 20-year-old student? What is the path to understand, to fill the gaps of this talk and to understand in details what you've done?
Okay, so the problem, so one problem is that this is it's a very technical kind of subject, and so the papers are quite long, and so it's easy, you can easily be discouraged by going on archive and looking up the paper and then seeing that it's 100 pages, and so there's a number of sort of review articles. So probably actually not a bad starting point is somehow the last 2 chapters of the book that we wrote with Peter Fritz. So the book is called A Course on Rough Paths. And so most of the book is on rough path, and that's read. The book is written in a very self-contained way. Most of the beginning is very elementary, and the last two chapters are on regularity structures in a somewhat non-technical way, sort of where it sort of gives you the statements, it gives you some ideas of the proofs, but it doesn't go into all the details. But I think it's sort of, I think that would probably be a good starting point if you want to sort of know about these things. And then you can also find there are several review articles that can be found on arXiv. I mean, if you just look at the list of articles, I think it's more or less self-explanatory which ones are the review articles and which ones are the technical ones.
Good. So then let's go to, so what's the problem in dimension? It's just the existence of these Wilson loops, or you have other problems in higher dimension?
Oh, so in high dimensions, okay, so first in this whole theory of regularity structures breaks down in 4 dimensions. So 4 dimensions is the critical dimension for YangMills. And so this construction, the type of construction that I've been talking about completely breaks down in 4 dimensions, which is very unfortunate, of course, because that's the most interesting one.
But why it breaks down in 4 dimensions?
It breaks down in 4 dimensions because so remember, the equation looks like, so there are terms like this, there are terms like this, and there are terms like this. And then there's the sort of noise. And if you look at the regularity, sort of how the solutions to the linear equation scales in dimension D, then it scales like, so A sort of scales like it belongs to C minus, what would it be? So it would be D minus 2 over 2. Right. And so in dimension 4, it means that it scales like, well, 4 minus 2 over 2 is minus 1, right? So A scales like C minus 1 in 4 dimension. That means that multiplication by A is actually just as bad as differentiation, right? So that's basically what this minus 1 somehow means, right? So differentiation makes you lose 1 degree of regularity. And so here, A itself also has sort of minus 1 degree of regularity. And that means that multiplication by A is basically equally bad as taking 1 derivative. And now what you see is that here, all these 3 terms are basically on equal footing, right? Because here you have A and you take 2 derivatives. Here you have A, you take 1 derivative, and then you multiply by A, which is again like taking 1 derivative. And here you have A and you multiply it twice with A, and so it's also like taking 2 derivatives, right? And so it's no longer the case that this guy is somehow dominant at small scales. Right? And so that's the reason why 4 dimension is sort of critical in this case. Yeah.
Then I have still another question is, well, in order to turn into a parabolic equation, could you add noise to your equation? Let's say it's a fast noise in the orbit direction, and just to smooth it out in this way, instead of using this trick by the Turk and Donaldson.
So it's not parabolic. So that will, right. So what you're thinking about, I think, is somehow at the level of the kind of Kolmogorov equation.
Yes.
Adding noise would sort of smoothen it out, right? But here you have the loss of parabolicity is sort of at the level of the equation itself, not at the level of the. So the Kolmogorov equation, if you want, that you would start from, so the one that's kind of problematic, which let me, right, so here, this one, this noise already acts in all directions. So it does act in this direction as well, right? So here, formally, the Kolmogorov equation is actually elliptic, right? Or parabolic, if you want. So the generator is kind of elliptic. but the equation, the PDE is not parabolic, right? So it's at one level above. It formally kind of looks like it's elliptic, but it's not the same type of regularization, right? So this is a sort of pathwise regularization of your connection, whereas the ellipticity that's given by the noise would be some sort of a regularization at the level of probability measures on the space of connections. Right? It's sort of one level above. So it's not really the same regularization. But I mean, but you're right. I mean, you could, for example, nothing prevents you from, for example, adding extra noise, or you could remove, right? So that's, I think, one idea that some people had, which would be to actually project the noise here onto the, sort of take only the component of the noise that's in this direction, right? To say, well, in this direction, the noise makes me wander around too far somehow. And so I just suppress it. I kind of remove this component of the noise and keep only that one. And that should make the equation better behaved from the analytical point of view. But that, first, it makes the equation look really messy. And also then you lose like Stromfeller property and stuff like that, which this equation actually has. And so you kind of lose the kind of regularization that you were talking about, which is actually useful here. And that one gets lost, of course, if you do the other thing.
Thanks. So now I'll turn to the questions of the audience. So let me tell you that we had more than 300 people following your lecture. So the first one, it's from Paulo Silveira. He asked, does Lie algebra work with continuous functions for class C2?
I'm not sure what.
I'm not sure what.
I'm not sure what the question is.
I'm not sure either. I can't. So maybe Paulo Silveira can try to make it more precise. So Eliazar Lozada asks, what applications have these results in quantum mechanics?
Well, so ideally, so if you were able to kind of push it all through, right? So if you were, so that's why there was a 2 words in the title of the lecture, right? Is that the program is not finished in some sense. If you were able to finish the program and to completely sort of build these measures, then you could sort of go back, do the sort of Osterwalder-Schrader kind of construction. You would have to justify that as well, of course, in this case, but I think one expects this to be doable. And then you would actually go back and have constructed an actual quantum field theory for YangMills. So if you could do that in 4 dimensions, which this approach is unlikely to be able to allow you to do, if you could do that in 4 dimensions, then you would have solved half of the YangMills millennium problem, I guess. The other half still being that you would have to still show that it has a mass gap. I think the probabilistic interpretation of the mass gap here would be that if you're able to actually construct this guy on all of RD rather than just the torus, then the invariant measure you get on all of RD should decorrelate somehow at large scales. Right? And if this decorrelates exponentially, then that would be the probabilistic analog somehow of the mass gap. So if you can then show that as well in 4 dimensions, then you've solved the YangMills millennium problem, I guess. But that's very, very far. I don't think there's any sort of I don't think there's any hope of doing that in this way in the next 5 years, say, or in the next 10 years, but maybe at some point.
So now we have a question by Leandro Chiarini. How explicit is the Banach space in the 2D case? Once the state space are found, do you follow the overall strategy of solving SPDEs in RD via regularity structures, or the strategy is fundamentally different?
Okay, so the state space, so that space of connections, it's completely explicit. I mean, I can say just a couple of words of how you define that space. So basically, the idea is it's sort of like, you know, when you define a space of distributions, you basically give yourself, you know, all the values of integrating your distribution against the test function, and this needs to be sort of compatible in the sense that it needs to be linear and so on. So here, what you do is you actually give yourself, you take sort of little line segments. So you look at all possible line segments on the plane, oriented line segments, and then you give yourself, you associate a number to each of these line segments, and you interpret this as sort of the integral of A along that line segment, right? It's a one form. A is a one form, right? So one forms can be integrated along lines or curves. And so here what you do is you give yourself a collection of numbers which you interpret, if you want, as the integral of A along each of these line segments. And of course, they need to be compatible in the sense that, you know, if you take that segment and you take that segment, then of course the sum of the two numbers needs to be the one that's associated to the, you know, segment you get by concatenating the two. And you need some kind of regularity in terms of, you know, it's not allowed, that number should sort of vary smoothly as you kind of move the endpoint and the starting point of your line segment, and you have to kind of specify precisely in which way this, you know, varies smoothly, and how big it's allowed to be as a function of the length of the line segment. So if A was an actual continuous function, for example, then the integral of A along a line segment of length, say alpha, no, alpha is bad because that's omega alpha, length L, would be about, at most, of size about L, right? Because if it's a continuous function, so here we take things where that number is allowed to be like L to the alpha for alpha a bit less than 1. And then that's the alpha that appears in here, right? So that's the idea of how you define that space. And then as far as the solution theory is concerned, at the end of the day, you do just apply, so to some extent, you just apply the black box for regularity structures. Of course, that space is very different from the kind of spaces you would look at there. But what you do is you show that, well, so what you know from regularity structures is that the solution to the nonlinear equation actually equals the solution to the linear equation plus something which is a continuous function. So the only reason why the solution is a distribution is because of the linear part of the equation. And then you just treat the linear part by hand. You kind of show that the linear part of the equation belongs to that space. And you show that adding continuous functions, you know, continuous functions belong to that space, and adding them, you know, is well defined as an operation somehow in that space. And so basically you just use the existing theory. In some sense, that's really not a large part of the work, right? So the solution theory is almost immediate. The only thing you have to work a bit is sort of looking at the linearized equation. Then the bit that you have to work more is the thing about showing that, you know, there is exactly one guy that has this gauge equivariance property. And that, of course, doesn't follow from the standard sort of regularity structure theory.
Perfect. Well, thank you very much, Martin. I think we have to close now our discussion because there will be another talk in a few minutes. Let me just remind that, can you write the name of Peter, so that they can find?
Oh yeah, the book is, well, there's only one book I wrote, so the co-author is Peter Fritz. And I don't think we even have a joint paper. We only have a joint book. So it's the only sort of written piece of work joined with Peter Fritz is that book.
So, and let me remind the audience so that we have people in Campinas with Paulo Rufino, in Bahia with Dirk Gerard, and in Brasilia with Alberto Rasch working in this area. So please contact them if you have further questions. So thanks a lot, Martin, for this very nice talk, and well, hope to see you soon.
Yeah.
Present in Brazil.
Yeah, I hope to see you in person soon and enjoy Geneva.
Thanks.
See ya.
Bye-bye.